And friends, seventh period, hopefully the third time is the charm. This is the period that I get to record. Third period, I lost my recording. Fifth period, it lost it. So, yeah. Yeah, well, it's recording off this right here, so it'll hear you guys backsplash noise, but that's about it. All right, so page 93, my friends, is what we will take a look at on our notes. And friends, I'm going to ask you to please, please, please trust me. And please, please, please stop me if something becomes the, huh? Does that make sense? Okay. So, everyone got page 93 going? Everyone ready? Yeah. All right, I'll dim the lights. Don't be scared. I kept the light on over here for Trent because I know he gets scared. Trent gets scared in the dark. Scared in the dark. Okay, you ready? All right, so we're going to go over a couple of definitions. These are not difficult things. You've done this before. So as everyone's on page 93 in your notes, yes? Yes. Okay, so first thing I wanted to define is I wanted to define a relation. I wanted to define a relation for you. So this is any graph or points that can be graphed, or let's go plotted. On XY axis. Okay? That doesn't seem too bad, does it? Any graph or points that can be plotted on the XY axis. Seems simple enough, right? Okay, so that's a relation. So if you can get to an XY axis and you can draw whatever shape you want, whatever dots you want, that's a relation. Basically, a relation means that I have anywhere from 1 to infinite amount of points that could be connected but don't have to be connected. That's a relation. Seem okay? So relations like the overall thing. If I had draw an XY axis and I put anything on that XY axis, it can be considered to be a relation. Okay? I'm spending a couple of minutes on because one, this is a tougher concept that it's going to be moving into, but I just want to make sure we're good. Everyone happy? Yeah. Okay. All right. So now this is a special relation. Okay. So this is like a subset. Relations like everything that you can put on the XY axis. Now we're going to call something a function. Any item graphed or plotted that does not have x values repeat. Okay? And we're going to call x values, we're going to start referring to them after we define a few more things. We're going to call it the domain. Okay? So, a relation is basically anything you could draw on the XY axis, anything to your imagination. A function is a special kind of relation that the x values don't repeat. Seem good? Okay, so just two different little baby steps. But we're going to build into more and more and more as we go on with this, okay? Okay, so a relation, anything that you could draw on the XY axis. A function, is anything you draw as long as none of the x values as points or as a graph or a picture repeats. Okay? Those definitions seem okay? May I move on? We're good? All right. So now, we're going to name a few items that are on the XY axis that go along with relations and functions. The domain are x values. Sometimes we call them inputs. The range are y values. Sometimes we refer to them as outputs. Okay, now, in science, you might have seen graphs or might have made a graph and you plotted it on an XY axis of some sort. Usually, they just have it happening in one of the quadrants. There's 4 quadrants in the XY axis. But the range are y values. The domain are x values. Now, if the domain repeats, then not function. Okay, so remember, a relation is anything you can draw on the XY axis. A special kind of relation is called a function. The function will not allow the x values, which now we're going to start referring to as the domain, will not repeat. Simple enough so far? Not too bad. May I move on? No. Okay. Life's better. Can you make the shoulders pop too? It's like, this is a good idea. Maybe I should start loosening up. All right. Ready? Yes. Here we go. All right, so now, these kind of look somewhat silly when we look at them. Okay? We have a t-table on the very far right, and then we have like these mapping systems that exist for the rest. All these really do is this is going to yield me the point 2, 4, 4, 8, 10, 20. So that's what all of these refer to. Squeeze it. So, do any of my x values repeat? No. Function? Yes. Yes. Good so far? All right, let's change colors. So this is going to give me 1, 20, 1, 8, and 4, 4. Does everyone agree with how I got those points? Yes. Do any of my x values repeat? Yes. Function? No. It's not a function. Okay. So relation, remember a relation is anything that you can plot on the XY axis, any picture, any dots, whatever. The function is the special relation that the x values don't repeat. Seem okay? Next problem. This gives me 1, 10, 2, 10, 3, 10, 4, 10, 5, 10. Do any of my x values repeat? No. My y values do though, right? It doesn't matter. Good. Thank you for picking that up. So this is a function. Okay? Now, later and further along math classes, there are actually special functions called one-to-one functions, and functions can be one-to-one and onto, so they get into smaller and smaller subsets. But right now, we're not worried about that. We're worried about, is it a function or is it not a function? Does the domain, the x values repeat, or do they stay the same? Okay? And then the last one, I think most of you have seen some sort of t-table. This refers to these points. Okay, do any of these x values repeat? Yes, the first and the last, yes? That's not a function, but it is a relation. Okay, still, it seems okay. And I'm going to get to a point where it's going to be like, whoa, what just happened? And will you stop me when I get to, whoa, what just happened? Please? Deal? You still trust me? I haven't really put anything that's like out of control. Oh, you? Oh, I'm sorry. So I haven't put anything that I think is really far-reaching. It's just kind of being able to understand, do I have points? What do these points have? Do the x values repeat? Repeating x values mean it's not a function, but it's still a relation. Okay? May I move to the next slide? Okay, now, you're all going to like this. This is going to be, I think, the easiest portion that you would ever come to on a problem. Like I always get frustrated when somebody misses these questions on a quiz. Vertical line test. A vertical line is a line that goes straight up and down. Agreed? Make sense? So the vertical line test is this. If I can pick any vertical line on any of my graphs, doesn't matter where the vertical line is. I mean, the vertical line can exist to the extreme left, to the extreme right, anywhere in between those. Agreed? If I can draw a vertical line test and it crosses through my picture more than once, this is not a function. The reason is, if I truly know how to draw a vertical line, these have the same x value. There is an x comma y, certainly, but the x value would be the same. If the x value is the same, that means it's not a function. If I were to give you one of these pictures on a test or quiz, say, is it a function, why or why not? Only thing you have to do on that very first one is say, it's not a function. Why? Why is it not a function? Did not pass the vertical line test. X values repeat. Something like that. That's pretty easy. Oh, look at that fun little circle. We like circles. But, I'm sorry, Mr. Circle. If I draw a vertical line, that vertical line is going to cross you twice, which, with my x and y values, that those 2 points could be defined as. And again, I don't know what those x, y values are exactly, but I know because they are on the same vertical line, that vertical line means we just took our fun circle and said it's not a function. The last one on the page, I could draw all kinds of vertical lines all day long. Okay? I don't have to just draw one. And each of those vertical lines are independent of each other, meaning one does not influence the other. But all those vertical lines, each vertical line only crosses my picture one time. So this one is a function. Okay? So let's review briefly. A relation is anything we can draw on the xy axis. Whatever picture you want. A special kind of relation is called a function. A function exists when the x values, which is also referred to as the domain, does not repeat. Vertical line test can also be used when looking at a picture. If the vertical line test, any vertical line is drawn on our graph, if that vertical line, at any one of those vertical lines, crosses my picture 2 or more times, that picture is no longer a function. It's still a relation, because a relation is anything I can draw on my picture. Okay? We seem good so far? Okay. Are you ready for the what? What? We good? Ready? Set? Okay. So, there's kind of a lot of information up here. And they can say, hey, function name is y equals 2x plus 3 a function? Why or why not? Things that you need to know right now. Now, there's other reasons why when you're looking at just a equation, why it wouldn't be a function. If I have the square root of y, okay? If I have y squared, or y to the fourth, or y to an even number, just by having that, that's going to say not a function. Okay? Y squared, y to the fourth, y to the sixth make sideways kind of parabolas. Okay? So, is y equals 2x plus 3 with what you know a function? Do we satisfy? Did any of those happen on the far right? No. So this is a function. That is a function. Okay. Now, if we know we have a function, we can write something called functional notation. Functional notation is just we replace our y value with f at x. So f parentheses x, this is called, we would say this in the terms, f at x. Okay? That means the same thing for the most part as y. And the reason why we start doing functional notation is that I can say f at x, g at x, m at x, z at x, f at x, capital F at x. Okay? Your sense function. We're just putting different labels. It'd be like this. Let's say you were all functions. Your first name, and your first name, and your first name, and your first name, and your first name are all different. So the f at x is just a way for me to say, hey, I'm dealing with a different function. Okay? That's all it is. So then, if we had function notation, this would be f at 6. Okay? If there was an x in there, we said f at x. Now we're going to say f at 6. All this means that we're going to do is I'm going to take the 6, and I'm going to plug it back in for the x. Now right above that 2x plus 3, 2 and x are being held together by multiplication. Okay? So f at 6, I'm going to take my above equation, and I'm just going to put parentheses. Inside those parentheses is where x used to live. Okay? But x is not going to live there anymore. We're going to go ahead and put 6 in there. So then 2 times 6 is 12, and 12 plus 3 gives me 15. So that's the answer to my problem. Seem okay? Bless you. Okay. Ready for me to do the last thing on this page? Are those both the same thing? F at x and f at x? So f at x up here equals 2x plus 3. f at x down here is equal to 6. F at x and f at x are the same thing. Agreed? So this means on this one that we're going to say 2x plus 3, which is the first f at x, is equal to 6. Okay, so I did not replace 6 for x. I set them equal to each other because they were both originally f at x. And then I could just solve this by doing the math that we had learned prior to this. Not too bad, is it? We're taking baby steps, and you're supposed to stop me when it's done. What? Is there any stopping me going, what? We're good? Yeah.
Are we going to have to convert fractions?
No, you. From here on out, you're allowed to keep them as improper fractions always.
Okay.
Can I move to the next page? Okay, so this is the next page. There's 8 different problems on this page. I'm going to highlight this one first, and that goes with this one, this one, this one, and I'm going to box that one in. So those 4 problems up there go with negative 3x minus 2. Okay? So what this means, on problem number 1, I'm going to replace x with a 1. On problem number 3, I'm going to replace the x with a 0. Problem number 5, I'm going to replace the x with a negative 1. And then this one, we'll get there in a second. Okay, so let's go through a little bit of the math to make sure we feel good about this. So this one I'm going to go, and I'm going to plug 1 in. And I get negative 3 minus 2, which is negative 5. Good. Next one, I'm going to do negative 3. In the parentheses was x, but I'm going to put a 0 there. Negative 3 times 0 is 0. Minus 2. 0 subtract 2. It's negative 2. What am I going to do for number 5? What do you think? Yeah, replace the x with negative 1. So in those parentheses was an x. Now it's going to be a negative 1. Negative 3 times negative 1 is positive 3. Subtract 2. Okay. I think you might feel comfortable with that so far. Friends, number 7 looks a little bit different than 1, 3, and 5. Agreed? What do you think we should do? What should we do? Am I going to put negative 8 in for x? No. I'm going to set negative 3x minus 2. I'm going to set it equal to negative 8. Do the math. It's done. Can you see how number 7 is slightly different than 1, 3, and 5? It's a different operation. Okay? All right, so now I'm going to deal with g at x. So I'm going to put this, this, and we're going to box in this one. So we're going to do the same thing, but we're no longer using f at x because we have the letter g. We're going to use the equation that is g at x. Okay, so I'm going to go 10 times 1 plus 2. Where that 1 is where x did live. Add those. Done. G at 0, 10 times 0. Because where the 0 is at is where x was. That's going to give me 0 plus 2. And then g at 1, 10 times negative 1. Where the negative 1 is where x used to live. Do the math. We get there. What should we do with number 8? Very good. 10x plus 2 is equal to 32. Subtract 2, subtract 2. Divide by 10. X equals 3. So 7 and 8 are a little bit different thought process, a little bit different problem solving skill than the others. Do we have any of the, wait a minute, scenarios? You feel comfortable? All right. Thumbs up. Where are you at? Thumbs up, middle, or down? I got a middle, middle to up, middle to up. Okay, middle to ups. Where can I help you? Be honest. You good? Happy to explain it. Okay. Again, this is a newer idea. It's going to kind of make your brain hurt a little bit, but I promise you it's not going to break. Just trying to build in a different math idea that will allow you to think at a higher level, critically thinking. Okay. Ready? Oh boy. You have 2 graphs up there. Okay? I'm going to do a couple things with the 2 graphs. Looks like we're going to ask about the domain and range, where it's increasing, where it's decreasing. What's our maximum, what's our minimum? I think those are all items that we're asking. Okay? This is where critical thinking is really going to start coming in. The domain is, we're looking at the very first graph. This is the graph I'm going to pay attention to right now. Domain are my x values, agreed? I read my domain, I will write it as interval notation, which we did on the last test. What does it appear on my graph is my furthest to the left x value? X value. Yeah. What do you think? Let's look right here. I'm just looking on the graph. What is my furthest to the left in the x direction? Yeah. 0? Okay, 0. 0 comma 70 is that point. So 0 comma 70, let me write that real quick. This point is 0 comma 70. Agree? Is it a solid dot or is it an open dot? Solid. So my domain is going to go from 0. Now, we're going to go as far to the right as we can on our graph in the x direction. What's the furthest to the right x value? Yeah. Furthest to the right. 60. Okay, so this is the point. It looks like 60 comma maybe like 142. I don't know. Do you agree that that point could be about that? Okay. Oh, and it shouldn't be a round dot, rounded. It should be a hard bracket because it's a solid dot. That is my domain of that function. Okay. I talked about the x values, furthest left to furthest right. Let's look at the range. I want to look for the range goes in the vertical direction. We go from the lowest, the very bottom, to the very top. So look at my y values on the graph. Which one do you think is the lowest one on the graph in the y direction? Not 0, 70. Good. And again, it's a solid dot, so 70. So we're talking about what's going on in the y direction, the vertical direction. What is my highest tippy top point that I can get to? It doesn't have to be at the end. Right here? Right there? Looks like 160. Now, where a graph changes directions, that creates a point. So that means that it's also a solid bracket. Okay? Now this is really different thinking. Okay? You're talking about what's going on in the x direction and then what's going on in the y direction. I'm going from the furthest left to the furthest right from the domain, the x value, to the lowest on my graph to my highest in the y direction. And I have to realize, is it an open dot or a closed dot? Corners, where a graph changes direction, is a high point. Okay. You feel comfortable with that? Okay. Now we're going to talk about where our graph is increasing. I'm going to highlight where it's increasing. I'm going to show where it's increasing, and then I'm going to try and tell you. So, it is increasing at certain segments. Increasing means as we go to the right, or as we go this way, is the graph pointing up along that region, or is it pointing down? If it's pointing up, it's increasing. Okay? It actually means the slope is positive. Okay. My critical thinkers. $80.05 maybe? $35, comma 90 maybe? $50, comma 160. Okay. Ready? So is my green line in three different regions of my graph? So using the domain, the x values, you're going to talk about where it's increasing. It's increasing from 0 to 15. It's also increasing from 20 to 30. And it's also increasing from 35 to 50. Now, I'm slightly incorrect on that, but right now I just want to have the point that you feel comfortable. Between these 2 points here, I have it highlighted green. So that's from 0 to 15. 0 to 15. Does that seem okay? And then it changes directions on this little tiny segment here. And then right here, between these 2 points, it's increasing. So from 20 to 30, it's also increasing. And then between these 2 points here, it's also increasing. So that's from 35 to 50. Wait. Do you feel comfortable with that? This is a big, huge idea. Okay? Are we okay? So, we're also going to talk about where this graph is decreasing. So each of those pink regions I've just drawn is where the graph is decreasing. So interval where it's decreasing, it looks like 15 to 20. 30 to 35. And 50 to 60. Okay, so let's look at the board real quick. These pink regions indicate it's decreasing. As I go to the right, it's going down at that point in time. So between these 2 points here, from 15 to 20, it's decreasing. Again, we're using the domain to describe what the graph is doing. Between 30 and 35, which we listed, it's also decreasing. And from 50 to 60, it's also decreasing. So increasing means as I go to the right, it's pointing up. Decreasing means as I'm going to the right, it's going down. This is a much different thought process. And it's going to take you a little bit to say, can I really grasp this concept? Okay. Now, letter E says we want a maximum value. So that's our Y value. So looking at our points, what is my largest Y value? I'll highlight my Y values. Which one seems like the biggest Y value up there? Yeah. Okay, that is a big one. I think there might be a bigger one. 160, yeah. That's going to be my biggest Y value. My minimum also goes with my Y value. So looking at those highlighted yellows, what is my smallest Y value of all those points? What's my smallest Y value? What do you got? I heard it. 70. Oh my goodness. This is a different thought process for sure. Okay? Now, friends, you have to trust me. I'm not going to saturate you with work. In fact, I'm going to give you page 95 and 96. Page 95 and 96. But I want you to do the odd problems. Friends, I know someone who made the video of all the odd problems posted on Schoology. And I get it, you might go home and say, I'm just going to watch the video, which is a little tiny mini lesson on this. But if you're still going, huh? You have to be able to bring it to me tomorrow to let me know. I have a question. I'm not sure how to do it. I want to do it right. I'll get you through it, my friends. I promise you.